Learning Outcome 2, Functions and Algebra, 12.2.7. A. Investigate and use instantaneous rate of change of a variable when interpreting models of situations, demonstrating an intuitive understanding of the limit concept in the context of approximating the rate of change or gradient of a function at a point. C. Determine the equations of the tangents to graphs. Welcome to another lesson in this series called Calculus. Magava will be helping us to solve our problems again today. Hello, Magava.
Hi there, everyone.
At the end of our previous lesson, we were busy trying to find the gradient of a tangent to a curve at a point on a graph, looking for increasingly better approximations. This is part of our journey of discovery into why and how calculus was invented. You will recall that I told you that two authors in the field described calculus as a branch of mathematics that was invented to describe situations. It was invented, they say, as a tool for mathematical modeling. I'm not going to remind you of everything that we have done in the previous lessons now, but I do want to remind you of more general description of our mathematical problem which we were busy with the last time we worked together. Our first objective was to find the coordinates of the turning point of a graph. We realized that we will know that when we know where the gradient of the tangent to this graph is 0. And so we developed the more general problem, namely to find the gradient of the tangent to a graph at any point on the graph. A challenge that was so big that mathematicians had to invent new mathematics to solve the problem, and that new mathematics they called calculus. More accurately, they called it differential calculus. By the end of this lesson, you should have developed a much better sense of a pattern that will help us with this big problem which challenged mathematicians several hundred years ago. In fact, you should be able to identify a pattern that will help us to determine the gradient of a tangent to a function at some point on the function. Right, let's pick up where we left off. Where did we get to last time?
Last time we said we wanted to determine the gradient of the tangent to this graph of y equals x squared at the point 1, 1. In other words, the gradient of this line here. But we discovered that this was pretty hard to do because we need 2 points to find a gradient, and we only really have one.
So like those mathematicians a long time ago, I suggested that we find the gradient of another line, an approximation to the line we are interested in.
What you suggested was that we find the gradient of this line, which goes through 1, 1, and 0, 0, on this enlarged version of that graph. And I then calculate the gradient of the line to be 1.
But you weren't very impressed with my approximation, and you suggested that we improve on it.
I wasn't impressed because that line just looks so different to the tangent line, which means that its gradient will be very different to the gradient of the tangent line. So I suggested that we take the 1 point and move it closer to 1, 1. Like in this picture, where we moved it to the point on the graph that has an x value of 1/2. That left us with needing to calculate the gradient of this new line.
Which is what I asked you all to do as part of your task at the end of the last lesson so that you would be prepared for today's lesson. Now, Magava, have you done what I asked?
I sure did.
Great. Would you mind doing that calculation for us?
Not at all. It's easy. This point here is 1, 1. And this one is 1/2. And 1/2 squared. Since the function is y equals x squared, so that is 1/4. To determine the gradient, I must calculate the vertical change and the horizontal change. The vertical change is 1 minus 1/4, which equals 3/4. And the horizontal change is 1 minus 1/2, which equals 1/2. Which gives me the gradient, which is 3/4 divided by 1/2, which equals 3/2, which is the same as 1 1/2.
Wow, that was really neatly done.
I told you it would be easy.
The gradient of this line is certainly a better approximation of the gradient of the tangent than our first attempt was. Looking at the diagram, you can clearly see that line is a lot closer to the tangent than the first one.
But I didn't think that the gradient of this new line was close enough yet.
You're quite right. We needed to keep trying to make an even better approximation.
Yeah, so I suggested we take the other point and move it closer to 1, 1 again. When we moved the point on the graph so that it had an x value of 3/4, it looked like this. It was a bit hard to see, so we had to zoom in on the graph. And you asked us to calculate the gradient of this line as part of our task.
That's right, MacGyver. Would you like to tell us what you calculated the gradient of that line to be?
Not at all. It was really easy because the steps are the same each time. Let me write it on the graph. The gradient is 1,75.
Excellent. So where do you think we should go from here?
I suppose from here on, we should repeat our steps, moving the other point closer and closer every time.
Right. And when we do that, we will be improving our approximation of the gradient of the tangent each time. But I want you to stop there and think with me for a minute.
Okay. What about?
About what we realized at the start. We realized that we wanted to know the gradient of the graph at the point 1, 1. But to find a gradient, we need to be given 2 points. Since the line only passes through 1 point, in this case the point 1, 1. It seemed like it would be impossible for us to find the gradient of the tangent line.
Okay.
But rather than giving up, we simply chose another point that meets the following criteria: that the point also lies on the graph, and determine the gradient of the line joining the new point and the point where we want the tangent to meet the curve. We call the gradient between those points an approximation of the gradient we want.
We improve our approximation by moving the other point closer and closer to our point of interest.
And by moving the points close enough together, we can get our approximation to be as close to the gradient of the actual tangent as we like. Even though it seemed at the outset it was impossible to find the gradient of the tangent.
Because we only had 1 point.
Correct. And yet we know that the tangent and its gradient must exist because we can draw it.
I think I understand the process, but I'm not sure if I'm confident in determining the gradient of the tangent yet.
Fair enough. I think we need to look at another case before you're going to feel confident about finding the gradient of the tangent.
What case is that?
Well, so far we have explored what happens to the gradient of the line as we move the second point closer to our desired point from the left. For the sake of completeness, we should also see what happens as we place the second point on the right of the point that we're interested in.
Okay. So is that what you've done here?
Absolutely. Let me show you what I've done. Here I've put in the point 1 1/2, 2 1/4. What I'd like you to do is to determine the gradient of the line through these 2 points.
You really are making me work hard. Well, let me see. This point here is 1, 1. And this one is 1 1/2, 2 1/4. To determine the gradient, I want to calculate the vertical change and the horizontal change. The vertical change is 2/4 minus 1, which equals 1 1/4. And the horizontal change is 1 1/2 minus 1, which equals 1/2. I can now calculate the gradient as follows, and it equals 5/2, which is the same as 2.5.
Thank you. Good job.
No problem. But can we avoid doing that again, please?
What I suggest we do now is drop a table of what we have found so far.
A summary of all my hard work.
Right. What we have here is a column with x values to the left of our point of interest, a column with the x values to the right of our point of interest. Fill in the gradients that we have calculated so far. Magava, can you do that for us?
This one corresponds to this graph where we found the gradient to be 1. Then this block corresponds to this graph where we found the gradient to be 1.5. Similarly, this block corresponds to this graph where we found the gradient to be 1 3/4. Finally, this block corresponds to this graph where we found the gradient to be 2.5. And the other values we haven't calculated yet are...
Let me save you a bit of work here. This value is 3 and this value is 2.25.
I think I'm starting to see the pattern here. Are these gradients getting closer and closer to 2?
It sure looks like it, but I don't think we should jump to conclusions too fast. To be absolutely certain, we would need to have a lot more values.
That sounds like a lot of work.
I have a surprise for you. Instead of us doing all the hard work, I have developed a computer spreadsheet to do all the calculating for us. This table looks just like the one we developed. Here in the heading we see that the table is for the function f(x) equals x squared, the one we are busy with. In this yellow cell is the x value of the point at which we are trying to determine the gradient of the tangent in our case 1. Down the left here, we have the x values of the other point on the left of our point of interest. You notice how close these points get to 1 without actually being equal to 1. In this column here, we have the x values of the other point on the right of our point of interest. Again, notice how close these points get to 1 without actually being equal to 1. Finally, in these blue cells, we have the values of the gradients between our point of interest and the other point, the approximation of the gradient of the tangent line, if you like.
That's fantastic. You asked the computer to do all my work for me. I just hope it did it as well as I would have.
Let's hope so.
These values get much closer to 1 than the values we worked with. And see, my observation is right. The approximate gradient is getting closer and closer to 2.
Yes, you were right after all, but we still needed to make sure. The power of this computer spreadsheet is that we can now repeat all of our work for any point on the function f(x) equals x squared by simply changing the value in the yellow cell.
Pretty cool. Can I try?
Sure, but I think we should leave this problem here for now. You can give it a go next time. Let's quickly go over what we have done today. In order to get a line which is closer to a tangent at the point 1, 1 than the line through the origin and 1, 1, we took the points on the parabola closer to the point 1, 1 than the origin and calculated the gradients between these points and 1, 1. Then we took 3 points to the right of our chosen point and calculated the gradients between each one of them and 1, 1. We arranged all these results in a table. This made it easy to observe that the gradient of the line joining 1, 1 to a chosen point on the curve approaches 2 as the x values of the chosen point approach 1 from the left and from the right. Then we set up a spreadsheet which produces the gradients for lines joining any chosen point on our parabola to points very close to the point. It calculates the gradients for 6 points to the right and 6 points to the left of any chosen point. The spreadsheet results confirm that the gradient of the tangent to the parabola at 1, 1 seemed to be 2. Now I'd like you to calculate a few more gradients for me. So for your task today, complete the two tables alongside for the function y equals f of x equals x squared and the points 2, f of 2 and 3, f of 3.
I'll definitely keep a lookout for any patterns and tell you about it next time.
I look forward to it. Till next time.